Hello and welcome to today's revision session on AQA A-Level Physics Paper 2. So in today's revision session, what we're going to be looking at is trying to answer examination questions found on topics on A-Level Physics Paper 2. So if we've been successful and learned in this revision lesson, we'll be able to answer A-Level Physics examination style questions for Paper 2. You can assess your own understanding on A-Level Physics and finally understand what topics we need to improve on moving forward for A-Level Physics. So, just a few things in terms of how I will carry out this revision session. Firstly, when completing your work in this revision session, divide your piece of paper into two sections and make the left hand side larger than the right hand side. So in the left hand section, you would write down your working out and answers to the questions in the revision session. Now when you're doing this, try and write your answers in full sentences and show your working out. But in the right hand side, write down any pieces of information you find useful or any hints and tips on answering questions from this revision session. So at the end of the revision session, write up these notes into a revision sheet for you to use independently. So let's start with answering some questions from A-Level Physics Paper 1. So the first topic we're going to look at is thermal physics. So look at the following question. Lead has a specific heat capacity of 130 joules per kilogram Kelvin. Now explain what is meant by this statement. And then lead of mass 0.75 kilograms is heated from 21 degrees Celsius to its melting point and continues to be heated until it all has melted. Calculate how much energy is supplied to the lead and give your answer to an appropriate number of significant figures. So pause the video now and then unpause the video when you want to go through the answer to this question. Right, so it's very important that firstly you know the definition of specific heat capacity, but then also relate it to the actual question. So don't just give the general definition of specific heat capacity, but rather incorporate the fact that it's of lead and it's 130 joules per kilogram Kelvin. So what this is it takes 130 joules to raise the temperature of mass 1 kilogram of lead by 1 Kelvin or 1 degree Celsius. Now because the difference in a Kelvin and a degree Celsius is the same, it's okay to use either in the definition. Also, if you're saying it's 1 kilogram, which is the definition of specific, because that's what specific means, 1 kilogram, you can also say per unit mass, because that's another way of saying that. Now in the next question, it's asking you to work out how much energy is supplied to the lead. Now it's very important when you look at this, you can notice that it's heated from 21 degrees Celsius to its melting point and then continues to heat it until it's all melted. So this tells us we're going to have to work out the energy for two separate sections. The energy needed to heat it up to the melting point, which is 327.5 degrees Celsius, which will be linked to the specific heat capacity, and then the energy needed to actually completely melt the lead, which will be linked to the specific latent heat of fusion. So you'll notice in the answer here that you're firstly working out the energy needed to raise its temperature, MC delta T, where delta T is the change in temperature, which you can see we can work out there, and then the second part, which is ml, which is the energy needed to melt the lead. So you can see the two values there, add them up to get the total answer. Now you'll notice in the question 0.75, 21, each is 2 sig, each at a 2 sig fig, so your answer should be to 2 sig fig, 4.7 times 10 to the 4 joules. Right, let's now look at another question. State two assumptions made about the motion of the molecules in a gas in the derivation of the kinetic theory of gases equation. Use the kinetic theory of gases to explain why the pressure inside a football increases when the temperature of the air inside it rises. Assume that the volume of the ball remains constant. So once again, pause the video now, then unpause the video when you want to go through the answer. Right, so first thing, it's very important that you do know your assumptions about the kinetic theory of gases. It was also important that they're bolded in the question motion. So anything that's not to do with motion, it won't be allowed in the answer for your answer to your question. So what about the motion? First thing, the molecules continue to move about in a random motion. We also know that the collisions of molecules with each other and the walls are perfectly elastic, so the kinetic energy is conserved, that the time in contact is small compared with the time in between the collisions, and then finally the molecules move in straight lines between the collisions. So you've got to be able to talk about that. Now don't fall into the trap of just doing general assumptions regarding the kinetic theory of gases. Let's now look at the second question. So what do we know pressure is? Pressure is related to the frequency of the collisions with the particles with the side of the football, and secondly how strong those particular collisions are. So it's the idea that the pressure is force over area, and therefore force is equal to the rate of change of momentum. So the point is, if the temperature has increased, that means that the kinetic energy, or the root mean square speed, or the average speed of the air molecules has increased. So there are more collisions with the inside surface of the football each second, and each collision has a greater change in momentum, so they all combine to produce a higher pressure. Always try and link it into the collisions of the particles with the surface, not with each other, with the surface. Let's have a look at another question. Explain what is meant by the specific latent heat of fusion. And figure 1 shows how the temperature of the water is maintained in a hot tub. The hot tub system has a volume of 4.5 meters cubed and is filled with water at a temperature of 28 degrees Celsius. The heater transfers thermal energy to the water at a rate of 2.7 kilowatts whilst a pump circulates the water. Assume that no heat is transferred to the surroundings. Calculate the rise in water temperature that the heater could produce in 1 hour. So pause the video now and then unpause the video when you want to go through the answers to the question. Right, so first thing is you've got to look at what the definition is of specific latent heat of fusion. Now remember, specific means per kilogram or per unit mass, and then it's asking about fusion. So you can't just give a general definition of latent heat, because it's asking about the latent heat of fusion, not vaporization. So our 2 marks are, it is the energy required to change 1 kilogram or a unit mass of material from a solid state to a liquid state, or it melts or fuses, because it's the same process just in opposite directions. Look, we've actually said what we mean by fusion. And then the second mark is that without a change of temperature, or it's at the freezing point or it's at the melting point, it's very important to state in your definition for latent heat that temperature remains the same. Let's look at the second question. Now again, we're trying to calculate the rise in water temperature that the heater could produce in 1 hour. So what we've got to do is as follows. We know that the energy is going to be mc delta T. Okay, and then we know that it's going to be in an hour. So what we can then do is we can work it through by saying, well, delta Q or delta E over delta T is equal to MC delta theta over delta T. So what you can then do is, if you look at your answer, you can then work out what delta theta, which is the change in temperature, is going to be. So it's going to be the change in energy over time times by the change in time over MC. Now it's important, why have we divided by time there? Well, it's because we're being given the energy, we're not being given the energy, sorry, we've been given the power in the question. So you'll notice in the question it gives you the power, not the energy. Now another way of doing it is you could work out the total energy transferred by doing 2.7 times 10 to the 3 multiplied by 3,600, because we know that it's going to be transferring 2.7 kilojoules every second, because that's the definition of a watt. It is 1 joule transferred every second. So in 1 hour we can work out what our total energy transfer is going to be by multiplying our power by the number of seconds. That's another way to do it, to work out what energy is, and then say E equals mc delta theta or delta temperature. So therefore delta temperature or change in temperature is going to be equal to E over mc, which you can work it through and you get 0.51 Kelvin. Now again, it's very important that we check to see our answer looks appropriate. And I mean, I think that a change in temperature of half a Kelvin, half a degree Celsius, is going to be appropriate when you think of the power is not very high in that particular heater for the size of it. Right, so let's have a look at a few questions now regarding electrical fields. So let's have a look at the following question. Figure 3a shows a stationary electron in a non-uniform electrical field. Figure 3b shows a stationary proton placed exactly in the same position in the same electrical field as the electron in figure 3a. State and explain how the electrostatic force on the proton in figure 3b compares with that on the electron in figure 3a. Each of the particles starts to move from the position shown in 3a and figure 3b. State and explain how the magnitude of the initial acceleration of the proton compares with that of the electron. Then finally describe and explain what will happen to the acceleration of each of these particles as they continue to move in the electrical field. So pause the video now and unpause the video when you want to go through the answer. Right, First one, it's the idea that it's the electrostatic force on the proton and the electron. Now they're in the same electrical field, so the forces will be equal in magnitude because they're in the same part of the same electrical field, but they're going to be in opposite directions because one is a negative charge and one is a positive charge. And remember, the electrical field has a direction based on the charge of the object. Now each of the particles starts to move. How will the magnitude of the initial acceleration of the proton compare with that of the electron? Well, you've got to remember again, we're still obeying Newton's laws of motion from paper 1, and we know F equals ma, so A is going to be equal to F over m. So therefore, even though both have the same value of F, the proton has a much bigger m, a much bigger mass, so therefore we can say the acceleration of the proton is much smaller than that of the electron because its mass is much greater. Next question. Describe and explain what will happen to the acceleration of each of these particles as they continue to move in the electrical field. Now, it's important to note that as they're moving through the field, their actual electrical field strength is changing. We know this because the lines are changing their distance between each other. The closer the lines are to each other, the stronger the electrical field, so therefore the stronger the electrostatic force. Now, again, it's important to note that the electron is going to be moving in the opposite direction to the field lines, because in electrical fields the field lines always point in the in the direction a positive charge would take. The electron is a negative charge, so will go in the opposite direction. So the electron is going into a weaker part of the field, whilst the proton, being a positive charge, will be going the other direction and will be going to where the field is stronger. So this tells us that over time the acceleration of the proton will increase because it's going to a stronger part of the field, but the acceleration of the electron will decrease because it's going to a weaker part of the field. It's very important to always remember that in electrical field diagrams, the field lines show the direction a positive charge would take. Let's have a look at another question. Figure 2 shows an electron at a point in a uniform electrical field. We know this because the field lines are constant distance apart from each other at an instant when it is stationary. So draw an arrow on figure 2 to show the direction of the electrostatic force that acts on the stationary electron. Then state and explain what, if anything, will happen to the magnitude of the electrostatic force acting on the electron as it starts to move in this field. So pause the video now and unpause the video when you want to go through the answers. Right, so what do we know? Well, the field lines show the direction a positive charge would take, and the electron is a negative charge, so it'll be in the opposite direction to that. So the arrow should be horizontal because that's the direction of field lines. That's the orientation of the field line, but it should be in the other way to the left. The next one is state and explain what will happen to the magnitude of the electrostatic force acting on the electron. Well, you'll notice as it's moving, the field strength stays the same because the field lines are the same distance apart. So therefore, because the electrical field strength is constant, the electrostatic force is unchanged. Let's have a look at another question. Define the electrical field strength at a point in an electrical field, and then figure 2 shows a point charge of plus 46 microcoulombs placed 120 millimeters from a point charge Q. Position P is on the line joining the charges at a distance 66 meters from charge Q, and the resultant electrical field position of P is 0. Calculate the charge Q. And then explain without calculation where the net work must be done in moving a proton from infinity to position P in figure 2. So pause the video now and then unpause the video when you want to go through the answers. Right, again, it's very important that in A-level physics you just know some key definitions, and you've got to know all the field strength, the field quantity definitions, such as field strength, potential difference, the laws, and such things like that. So what's the electrical field strength? So the first one is it's the force per unit charge. Remember, field strength is force per unit property of the field. So if it's a gravitational field strength, it's the force per unit mass. So it is the force per unit charge on 1 mark, but then remember that for all electrical field definitions we define it in terms of positive charges, because remember the field lines go in the direction a positive charge would take. So therefore it is the force per unit charge on a test positive charge, or a sample positive charge, or a unit positive charge. Question 2. Again, this is quite a lot of information to decode, but the first thing you've got to remember is that about point P, the field strength is 0. Now, because the field strength is a vector quantity, that tells us that the field strength from Q and the field strength from the other charge, plus 46 microcoulombs, must have a field strength that cancels each other out exactly at P. So what you can therefore say is as follows. We know what the equation is for electrical field strength. It is Q over 4 pi epsilon 0 r squared, which is r being the separation from the point we're looking at. So we know that on the right hand side here on this diagram, it's going to be 46 times by 10 to the minus 6, because remember the micro is going to mean, sorry, the micro there is going to mean minus 10 to the minus 6. So it's 46 times 10 to the minus 6 divided by 4 pi epsilon squared, epsilon r squared. Now what's r going to be? Well, it's going to be 120 millimeters minus 66 millimeters, because that's the actual distance that charges from P. So therefore we can see it's going to be 0.054, and then you know the other side it's going to be Q, which we don't know, over 4 pi epsilon 0 r squared. Now r in this case is 66 millimeters, so we convert that to meters because we work in meters in A-level physics. So it's then 0.066 all squared. You can therefore see on our screen now that when we have this equation, there's only one unknown, Q. So at this point you then rearrange the equation to make Q the constant. Now the savvy amongst us will realise that when we rearrange this, there's going to be a 4 pi epsilon squared at the top and at the bottom of the equation, so they cancel through, which is why they're not present on the second line. Then your answer is going to be 6.9 times 10 to the minus 5 coulombs, or 68.7 microcoulombs, which again looks right because it's balancing out 46 microcoulombs on the other side, but that one is in fact, let's get this right, it's going to be slightly, it's going to be slightly closer, so it is going to have to obviously be slightly stronger at Q because it's slightly further away, so it does make sense. Next one, explain without calculation where the net work must be done in moving a proton from infinity to position P in figure 2. Well, let's think about this. Work will have to be done on a positive proton because P is at a positive potential. You can see that in the actual situation, it's at a positive potential. So therefore work has to be done to overcome the repulsive forces because the like charges repel, and then we start with our potential at infinity. That's a very, our potential at infinity is 0. That's a very important thing you've got to remember. So basically if you're starting at infinity and it's a positive charge and you need to move it to a positive charge, well, you need to put energy into the situation to overcome the repulsion of a positive, and if you're starting at 0, you've got to put something in there to get it to that point, so work has to be done into it. Again, it's very important you always remember that we define that the potential at infinity for any gravitational field is 0. So therefore if you are trying to put something into the field and it naturally is repulsive, you need to put energy in. Right, so let's have a look at a couple of questions now on capacitance. So figure 2 shows a capacitor of capacitance 370 picofarads. Remember what pico means. It consists of two parallel metal plates, areas of 250 centimeters cubed. Again, remember what centimeters cubed are. We need to convert those to meters cubed later, and think about it, centimeters cubed to meters cubed is not the same as centimeters to meters. A sheet of polythene has a relative permittivity of 2.3, completely filling the gap between the plates. So for 2 marks, calculate the thickness of the polythene sheet. Right, so pause the video now and then unpause the video when you want to go through the answer. So first thing is, we know it is a parallel plate capacitor, so you've got to look up the equation from the equation book, and our equation will link into, I believe, okay, it's the idea of making D the subject here, but we do also know from our equation book that C is going to equal, let's get this right off the top of my head here, it's going to be the it's going to be the capacitance. So the capacitance is going to equal those values, the values of the relative permittivity and the permittivity of free spaces in there, and the distance between the two plates is in there, and the area between the two plates is in there also. So we can rearrange that equation now, and we can rearrange the equation to work out the thickness of the polythene sheet, which is the distance between the two plates. So therefore you make d the subject, and then you pop in your values. So you go, it's 8.9 times 10 to the minus 12 times by 2.3 times by 250 times 10 to the minus 4 over 370 times 10 to the minus 12. Where do all those numbers come from? Well, 8.9 times 10 to the minus 12 is going to be the permittivity of free space. We know 2.3 is the relative permittivity given in the question. We know that the area is 250 times 10 to the minus 4 because centimetres to metres is 10 to the minus 2. So centimetres squared to metre squared is 10 to the minus 4. And therefore you divide that by 370 times 10 to the minus 12. Now again, why is that? It's because pico is 10 to the minus 12. Pop all the numbers in and you get 1.4 times 10 to the minus 3 metres. What's the most important thing you've got to do once you've worked out an answer for a question in A-level physics? Well, it is you've got to check to see if the value looks sensible. So it's 1.4 millimetres. That looks about right. That looks something sensible. So probably is going to be right. Right. Let's have a look at a few questions on magnetic fields. So, figure 3 shows an arrangement for investigating the electromagnetic induction. When the switch is closed, there's a current in the coil in circuit X. The current is in a clockwise direction as viewed from position P. Circuit Y is viewed from position P. Explain how Lenz's law predicts the direction of the induced current when the switch is open and again when it's closed. So pause the video now and then unpause the video when you want to go through the answers. Right. So, what do we know? Well, we know from Lenz's law straight away that induced current must be in the opposite direction to the change that causes it. So, the important thing to note is that when you switch on the circuit, the current increases through the flux through Y. So, therefore, the current will be in the opposite direction to this to create an opposing flux. But when you switch off the flux, the current through Y due to X decreases. So, the current travels clockwise to create a flux to oppose the decrease. Remember, electromagnetic induction always occurs when there's a change in flux linkage. Now, it doesn't matter if it's a positive change, i.e. turning on the circuit and putting a current through the electromagnet, or a negative change, i.e. turning off the switch as well. A number of people, when answering questions, only talk about a positive increase in flux, a positive increase in the flux to produce a EMF. However, remember, for electroinduction, both a positive and a negative change would create this EMF. Right. Let's look at the next question. The Large Hadron Collider uses magnetic fields to confine fast-moving charged particles travelling repeatedly around a circular path. The LHC is installed in an underground circular tunnel of circumference 27 kilometers. In the presence of a suitably directed uniform magnetic field, charged particles move at a constant speed in a circular path of constant radius. By reference to the force acting on the particles, explain how this is achieved and why it happens. The charged particles travelling around the LHC may be protons. Calculate the centripetal force acting on the proton when travelling in a circular path of circumference 27 kilometers at 1/10 the speed of light. Ignore relativistic effects. So once again, pause the video until you want to go through the answers and then unpause the video. So, let's have a look at the answers. So, it's an important idea to note the following. Okay, explain why they move at a constant speed in a circular path. Well, the magnetic field is applied perpendicular to the path. It's very important that you always remember in a particle accelerator such as a cyclotron, the magnetic field acts perpendicular to motion and the electrical field acts parallel to motion. So therefore, if the magnetic field acts perpendicular to motion, it will act as a centripetal force. So we know that the charged particles have a magnetic force acting perpendicular to the path, so it acts as a centripetal force. So it provides a centripetal acceleration towards the centre of the circle. It links back into those topics we covered in paper 1. Now we know that the magnetic force is BQV. We also know that the centripetal force is mv squared over r. So therefore what we can do is we can equate the two because the magnetic force is the centripetal force. We can equal them and make r the subject. So r is equal to mv over bq. You're not given that equation in your examination book because it's important that you can link the two together, that in the actual application of particle accelerators the magnetic field is the centripetal force. So r is equal to mv over bq, and in this case we know the Large Hadron Collider r is a constant, so that tells us that b and v must also be constants because the value is staying the same. Next question, let's see if we can work it out. Well, we know that the radius of the path of the actual particle accelerator is going to equal to circumference over 2 pi. That's an equation you learn in GCSE mathematics. So therefore we know the circumference is 27 times by 10 to the 3, because we work in meters, not kilometers, divided by 2 pi, so it's 4.30 times 10 to the 3, and therefore we can work out our centripetal force. Now again, you can just use the general centripetal force equation, so it's mv squared over r. So it's therefore, you pop in the values. Now again, you know the mass from the equation book, and then you know what v is from the question. It's a tenth the speed of light, so it's going to be 3 times 10 to the 7, and then you square that because it's mv squared over r. You've got your value of r, and you get 3.50 times 10 to the minus 16 newtons. Again, read the question carefully. A lot of people, when answering this question, will just pop in the circumference as the radius. It's not. So always read the information carefully in your question. Let's have a look at another question. Calculate the flux density of the uniform magnetic field that will be required to produce that previous force. Then state an appropriate unit. And then the next one is the speed of the protons gradually increases as their energy is increased by the Large Hadron Collider. State and explain how the magnetic field in the LHC must change as the speed of the protons is increased. So pause the video now and then unpause the video when you want to go through the answers. So what do we know? Well, now we can link it back in, because we've got magnetic flux density is what we need to find an answer for, into that magnetic force equation. Because if we use the centripetal force, F equals mv squared over r, well, there's no term for the magnetic flux density in there, so you can't use it. So we're going to have to use F equals bqv. So therefore B is equal to F over qv. You've got your value of F from the previous question. You've got Q because you know the charge, because it's a general known value, so it's 1.6 times 10 to the minus 19. Which is why it's always important to know your key values, such as the charge of protons and electrons. And then you times it by the velocity, which we know is 3 times 10 to the 7. So our answer is 7.29 times 10 to the minus 5. And again, it's always important you memorize your different units. It's the Tesla. So there's your answer. Then the next one, the speed of the protons increases as the energy is increased by the LHC. State and explain how the magnetic field in the LHC must change as the speed of the proton is increased. Well, we know from our previous work that R is equal to mv over bq. Now, in this Large Hadron Collider, you need to keep the radius the same, otherwise the particle is going to hit against the side of the accelerator, which you don't want because it'll lose energy. So we know if R equals mv over bq, well, therefore, if the velocity is increasing, B must increase at the same ratio to therefore keep R constant, because if V is increasing, B must also increase. When the two divide by each other in the equation, R is kept the same. So the magnetic field must increase at the same rate as the velocity is increased. It's a very common question to ask in A-level physics exams, to talk about particle accelerators and this equation, R is equal to mv over bq. Again, you should be able to derive this from first principles, but it's not given to you in your examination equation book. So let's now have a look at a couple of questions on nuclear physics. So figure 3 shows how the binding energy per nucleon varies with the nucleon number. Fission and fusion are two nuclear processes which energy can be released. Explain why nuclei that undergo fission are restricted to a different part of the graph than those that undergo fusion. So pause the video now and then unpause the video when you want to go through the answer. So what do we know? Well, fission occurs at A values above the peak or above A56, and fusion occurs at values below the peak or below A of about 56. That's because we know that fission is the splitting of a nucleus into smaller ones, and fusion is the joining of the two nuclei. So if you look at this particular graph, the aim of any nuclear process is to increase the binding energy per nucleon. So you'll see that once you get to about 56, which is iron and the nucleon number, that it tails off, and before iron at 56 it's below it. So in both processes it needs to get to the highest possible value, which is iron at 56. So everything below iron will carry out fusion, so it will combine to get bigger, whilst everything above iron will carry out fission, so it then will split to then get to 56, which is what's going on here. Let's have a look at another question. Explain with reference to figure 3 why the energy released per nucleon from fusion is greater than that from fission. So let's have a look at that unit again there. and then calculate the mass difference in a kilogram of the oxygen nucleus, and then using the answer from the previous question, calculate the binding energy in MeV of an oxygen nucleus, and then explain how the binding energy of an oxygen nucleus can be calculated with the information obtained from figure 3. So once again, pause the video now, and then when you want to go through the answers, unpause the video. So, what's going on here? Well, you'll notice from that diagram that the line below 56 has a lot steeper inclination than the line after 56. So this tells us that the energy is released when the binding energy per nucleon is increased. Now, fusion has a greater rate of increase in binding energy per nucleon than it has for fission. That's because there's a greater gradient, there's a higher steepness in the fusion part of the section of the graph than as opposed to the fission part. So the fission has a more gentler gradient, as you can see in the graph here. So calculate the mass difference. So how would you work it through? Well, you can work out your mass difference by working out the mass of 8 protons and the mass of 8 neutrons, and then you would subtract the mass of the actual oxygen nucleus from that. Now you can work out that there are 8 protons and 8 neutrons there from the information given in the question, because 16 is protons and neutrons, whilst 8 is the number of protons, so there's 8 protons, 8 neutrons. Now what you can do is you can work in values of U, because it gives you the mass of the nucleus in U. Now again, you are given the mass of a proton in U on the equation book, so please have a look, and the mass of a neutron in U in the equation book, so please have a look. You add the two together, then subtract it, so you get a change in mass of 0.1366 U. You can then convert that into kilograms, because the conversion factor from U to kilograms is 1.661 times 10 to the minus 27 kilograms. So your answer is 2.3 times 10 to the minus 28 kilograms. Now you can calculate your binding energy in MeV. So how would you do that? Well, there's a few ways you can do that. There's two possible ways. You can either do the equation E equals mc squared with the mass in kilograms. So therefore you'd say E is equal to the mass in kilograms, which we've worked out to be 2.3 times 10 to the minus 28 times by the speed of light squared, which gets us to 2.07 times 10 to the minus 11 joules. We can then convert from joules into MeV by dividing by 1.6 times 10 to the minus 13. Now remember, 1 joule to 1 EV is going to be divided by 1.6 times 10 to the minus 19, but because we work in MeV in this question, it's 10 to the minus 13. So we get an answer of 130 or 129 MeV. But there's also a shortcut way to do this, because what you can do is you can memorize that actually the conversion factor between U and MeV is 931.3, and that's just a fact you'd have to remember for an exam, because it's not written down anywhere on the examination equation book. But you can convert from 1 U to goes into MeV by multiplying by 931.3. So you would do 0.1366 times by 931.3, which is 130 MeV. Now finally, explain how the binding energy of an oxygen nucleus can be calculated from the information obtained from figure 3. Now the important thing to note is on this graph, it's binding energy per nucleon. So what you would do is you'd read off the binding energy per nucleon for oxygen, the oxygen nucleus, and then you multiply by the number of nucleons to just get the total binding energy. So it would be 8 MeV from the graph multiplied by 16, which is approximately 130 MeV. Let's have a look at another question then. So, state what is meant by the binding energy of a nucleus, and then when a uranium nucleus absorbs a slow-moving neutron and undergoes fission, one possible pair of fission fragments is technetium and indium. Complete the following equation to represent this fission process, and then calculate the energy released in MeV when a single uranium nucleus undergoes fission in this way. So pause the video when you want to, and then when you want to go through the answers, unpause your video. So in this question, it's very important that you know your definition of binding energy. So binding energy is the amount of energy required to separate a nucleus into its separate neutrons and protons, or its separate nucleons, or into its separate constituents. I always remember it because it comes across as the opposite from the actual words, because we assume binding means to bring together, but in this context, binding energy is the energy needed to separate a nucleus into its individual constituents. The next question, what's always very, very important, is you've got to know that the numbers at the top will balance with before and after the arrow, whilst the numbers at the bottom will balance before and after the arrow. So for example, if we know it's 236 before, it's going to be in total 236 afterwards, and if it's got to be 92 before at the bottom, it's going to have to be 92 afterwards. So what do we have here? We would have, if you notice, that there's 92 before and there's 92 afterwards without anything in, so it's going to have a 0 at the bottom. And then what do we have? We have 236 before, but afterwards at the minute we've only got 234, so therefore we need a 2 at the top. Now there's no actual a constituent there which will have just a 2 there, so you're going to have 2 1s, so that's a 1 at the top and a 0 at the bottom, so therefore it is 2 neutrons. So you can see it there. Now again, calculate the energy released in MeV when a single uranium nucleus undergoes fission in this way. So what you've got to do is, you know the binding energy of uranium, because you would multiply the binding energy per nucleon by the number of nucleons, and it's given in the question above how many nucleons you've got, 235. So it's 235 times by 7.59, which is 1784. We know the binding energy of technetium by doing 112, the number of nucleons, times by its binding energy per nucleon, 8.36. And we do the same for indium, 122 times by 8.51. Then you subtract one from the other, so it's going to be 1975, which is the total of technetium and indium, minus 1784, so it's 191 MeV. Let's get you your answer. Let's have a look at another question then. So calculate the loss of mass when that uranium nucleus undergoes fission in this way, and then sketch on the graph a neutron number against proton number for stable nuclei. So pause the video now, then unpause the video when you want to go through the answer. So what do we do? So again, there's two processes you can do. You can either do E equals mc squared, so you can convert your value of energy from MeV into joules by 1.6 times 10 to the minus 13. Remember, not 19, because we're going from MeV to joules. And then we can therefore say, well, m is equal to E over c squared, so we can then work that out to be 3.4 times 10 to the minus 28. Or we can take the shortcut we talked about before, because remember we said the conversion from MeV to U is 931.5 or 0.3. So what you then do is you then divide this time by 931.3, which therefore equals 0.205 U, but the answer is wanted in kilograms. You then convert from U into kg by times by 1.661 times 10 to the minus 27 to get 3.4 times 10 to the minus 28 kilograms. So just remember that. Okay, now for the next one, we're going to have to sketch the graph. Now it's important to note that it is a straight line up to about z equals 20, and then when you get higher than that, it then starts to curve upwards slightly, some concave curvature. That's because remember that the larger nuclei to be stable require more neutrons, because the strong force doesn't work over the entire nucleus when it gets bigger and bigger and bigger, because it has a limited range. So to compensate for that, to increase stability, you need to have more neutrons compared to protons. So you're going to have that curving upwards to include more neutrons. Let's look at the next question. With reference to figure 1, explain why fission fragments are unstable and explain what type of radiation they're likely to emit initially. So pause the video now and then unpause the video when you want to go through the answers. So fission fragments are likely to be above the line of stability, because if you notice that there's going to be an excess in the number of neutrons, they're going to have a larger neutron to proton ratio than a stable nucleus, or they are neutron rich. So therefore you're going to have to think of the process that will take place if they have too many neutrons. So they're going to have to turn neutrons into protons, which you should hopefully know is the beta minus decay. Again, a common mistake people make is that they just say it's a beta emission. You've got to say it's a beta minus emission, because there's also the beta plus emission, but that would not be appropriate in this case, because beta plus turns a proton into a neutron, so that would even make it even more unstable, so that would not take place. Let's have a look at the next question. The carbon content of living trees includes a small proportion of carbon-14, which is a radioactive isotope. After the tree dies, the proportion of carbon-14 in it decreases due to radioactive decay. The half-life of carbon-14 is 5,740 years. Calculate the decay constant in years to the minus 1. Then a piece of wood is taken from an axe handle found on an archaeological site, which has 0.375 times as many carbon atoms as the equivalent mass of living wood. Calculate the age of the handle in years. years, then suggest why the method of carbon dating is likely to be unreliable in the sample if it's less than 200 years old or more than 60,000 years old. So pause the video now and then unpause the video when you want to go through the answers. So firstly, you've got to know the link between half-life and decay constant. The decay constant is equal to log 2 over the half-life, so quite simply do 0.693 over 5,740, so you get 1.2 times 10 to the minus 4 years to the minus 1. Now because they wanted the answer in years to the minus 1, you didn't need to change your value of time into seconds, but you would do if we wanted in seconds to the minus 1. Next question, you then got to use the equation n is equal to n0 e to the minus lambda t, or a is equal to a to the 0 e to the minus lambda t. So what you would then do is you would want to find out the value for t, because you know the value for a and you know the value for a0, so you can work it through. So you can work it through like that, and remember, if you want to take an exponential down to work it out, you're going to have to use the natural log. So it's very, very important you understand how to then convert from the natural logs and the exponentials. So t is equal to log of 1 over 0.375 divided by 1.21 times 10 to the minus 4, which is 8,100 or 8,200 years. Now for the next question, it's very important you know the limitations of radioactive decay dating for very young objects, well, in terms of age, and then the very, very much more ancient objects. So why would it be difficult for less than 200 years old? Well, it's because there wouldn't be a great change in activity, because there's not been much change in how quickly the decay is happening, because it's not even carried out a half-life yet. So therefore, less than 200 years old, okay, is going to be a small change in activity or count rates to be very difficult to detect. And then if you have it more than 60,000 years old, well, therefore the activity will be very, very, very small, because most of it already decayed, or you would probably say it's comparable to the background radiation. So therefore you're actually uncertain about how many carbon-14 atoms are left. Let's have a look at another question. A chain reaction is maintained in the core of a thermonuclear reactor that's operating normally. Explain what is meant by the chain reaction, naming the materials and the particles involved. Then explain the significance of critical mass in the operation of a thermonuclear reactor. And then substantial shielding around the core protects nearby workers from the most hazardous radiation. Radiation from the core includes alpha and beta particles, gamma rays, X-rays, neutrons and neutrinos. Explain why the shielding becomes radioactive. So pause the video now and then unpause the video when you want to go through the answers. Right, so first one, what is the chain reaction? So what's going on in a fission reactor? So you've got to know this process off the top of your head. So it is a uranium nucleus will capture a neutron and then split into two smaller fragments, releasing more neutrons. Again, remember, it's neutrons that are released, and then at least one of these neutrons will cause more fissioning or splitting of the uranium nucleus. It's very important you say it's the nucleus and not the atom, because it's in fact not the entire atom that is going to do this, only the nucleus that will be affected in such a way. Explain the significance of the critical mass. Again, you've got to know what the critical mass is, because the core must contain a critical or certain minimum mass of uranium or fuel. That's so in order for the neutrons from the fission of a previous event to then find another uranium nucleus to sustain that chain reaction. If it's below the critical mass, it's unlikely to actually find another uranium nucleus to then cause it splitting again. Now, you could then talk about from the other way if you wanted to, and say if it's below the critical mass, that means that there's not enough uranium there, so many of the neutrons escape and don't hit another uranium nucleus. How does shielding become radioactive? You've got to understand this process. So it's the neutrons that are absorbed and collide with the shielding, and then they convert the nuclei of the atoms into unstable isotopes when they would then become radioactive. Remember, in many nuclei, they are radioactive because they contain many more neutrons compared to protons. They're above the line of stability. So in fact, they are neutron rich, so they will become beta minus emitters. You've got to really understand that. That's how the majority of materials become radioactive. Next question. State and explain the results of the scattering experiment, including the main observations, the significance of each observation, and how the observations place an upper limit on the nuclear radius. So pause the video now and then unpause the video when you want to go through the answer. Well, again, for this one, it's important that you discuss each bullet point separately. So what I would do if this was me answering the question is I would answer the main observations in one paragraph, the significance of each observation in one paragraph, and how the observations place an upper limit on the nuclear radius in one paragraph. So we don't want to be working on a low level, we want to be or an intermediate level, we want to be working on a higher level. So what you need to do is you need to talk about all the observations, you need to talk about the significance of each one, and then interpret how they link into the upper limit on the nuclear radius. So let's take each one at one point. So it's the idea that most alpha particles will pass straight through. We know that from the scattering experiment, which suggests the atom is composed mostly of empty space or open space. We then know that alpha particles can be backscattered or scattered by more than 90 degrees, which suggests that they've collided with much more massive than themselves, because if they go to backscatter using momentum considerations, it's got to be something more massive than themselves. They've been repelled by a positive charge, the Coulomb repulsion. So therefore, we've got to think about what that could be. So it has to be a positively charged nucleus. You're then going to consider the proportion of the alphas passing straight through the foil, so you can then work out how big this nucleus is going to be. Or the accretion of the scattering of the alpha particles close to 180 degrees takes place very rarely, so therefore only I think 1 in 10,000, so you can then work out that's going to be quite small in size. But also as well, it's the idea of why is backscattering occurring. Well, backscattering is occurring because all of the kinetic energy is being transferred into potential energy, electrical potential energy, because they are the same charge, the nucleus and the alpha particle. So what you can then do is you can say the kinetic energy is equal to the gain in electrical potential energy, and this therefore will allow us to work out how close our alpha particle can get to the nucleus. Now remember, it is unlikely to actually hit the nucleus, because it's going to have converted all of its kinetic energy into electrical potential energy before it actually hits the nucleus. So therefore it gives us an upper limit on the size of the atomic radius, because it's going to be getting close to the so the nuclear radius, not the atomic radius, it'll be getting close to the nucleus, but it won't actually hit it. So it gives a value for the nuclear radius larger than it should be. Now it's important to then so always remember that when you're considering the Coulomb idea, the idea that it is the converting kinetic energy into electrical potential energy, that it's in fact not going to hit the nucleus, so it provides a larger value for the nucleus radius than you would do if you actually worked out by other methods. Let's have a look at another question then. Two hydrogen nuclei fused to produce deuterium as shown. Determine the amount of energy released in this reaction. So what you would do is as follows. So pause the video first, and then when you want to go through the answer, unpause the video. Right, so what do we need to do? We need to work out the difference in mass from before and afterwards, because that's the information we've been given in the question. So you work out the mass before and the mass afterwards, and then you work out the difference between the two, and the difference is going to be 8 times 10 to the minus 31 kilograms. Now because we are in kilograms, we can then do the equation E equals mc squared to work out the energy. So you then do E is equal to 8 times 10 to the minus 31 times by c squared, gets you 7.2 times 10 to the minus 14 joules. Let's have a look at another question. So this question is about the Rutherford scattering experiment. The nuclear radius cannot be bigger than the distance or closest approach of an alpha particle. Complete figure 2 to show the paths followed by each alpha particle. So pause the video now, and then unpause the video when you want to go through the answer. Right, so we need to think about all three lines here. So the top line of the alpha particle there is nowhere near the nucleus, so it's going to be unaffected. Now the one in the middle look like it's on a collision course. So what will happen is it will be backscattering, it will reflect backwards. Now it's important to note it does not actually touch the nucleus, because what's happening, like we said before, is that the kinetic energy of the alpha particle is converting into electrical potential energy, and then you'll have the repulsive effect to take over, so it will come very close, slow down, and then repel backwards without actually touching the nucleus. It's not a collision, it's in fact a repulsion of positive and positive charges. And then finally the arrow at the bottom is very close, but it's not hitting the actual nucleus, so what this one will do is it will deflect it will deflect away, but it's important to note that it's got to have a much stronger deflection than any one possible at the upper one, because it's a lot closer. And remember, the closer objects are with charge, the more they are affected by the actual electrostatic force, so you have a greater deflection. So you'll see the top path, little or no deflection, middle path reflected along its own path with not touching the nucleus though, and then finally the bottom one will be deviated but much more than that of the top one. Let's have a look at another question then. So the thallium nucleus is formed in an excited state. Electromagnetic radiation is emitted from the thallium atom following its formation. Explain the origin and location of the two sources of this radiation, and then other nuclei also emit electromagnetic radiation. Explain why the metastable form of the isotope of technetium is a radioactive source suitable for use in medical diagnosis. So pause the video now and then unpause the video when you want to go through the answer. Right, so let's have a look. So you need to understand when electromagnetic radiation is emitted from an atom. Now it's important to have said atom here, because that now means it's not just the nucleus. So there are two sources of this radiation. Source one is when orbiting electrons will fall from one energy level to another energy level, and then will release electromagnetic radiation, which is equal to the difference in the energy levels. Don't forget about that. And then secondly, an excited nucleus can also release gamma radiation, which is a type of electromagnetic radiation when it is de-exciting, when it is just relaxing. So they're the two possible answers. Now explain why the metastable form of the isotope is radioactive, is so suitable for medical diagnosis. Well, think about it. We've just said it's going to be emitting gamma radiation. So because it's emitting gamma radiation, they're weakly ionizing and can cause less damage to the body than other radiation. And the other important thing is it can also travel through the body and escape the body very, very easily. So it allows us to detect it when we're using it out, when we have our detectors outside of the body. The other things which you've always got to be aware of as well is that the actual source, technetium, has a low toxicity, and the half-life is short enough not to remain in the body for too long after the medical examination. So it's long enough to complete the diagnosis, but it isn't actually going to stay in there long enough to then cause harm, unnecessary harm. And finally, it can be prepared in the hospital or close to the hospital, because it's the samples you can handle very, very easily. So that concludes the revision session we've carried out today on A-Level Physics Paper 2. So hopefully from this revision session you can feel like you can answer A-Level Physics examination style questions, you can assess your understanding on the different topics in A-Level Physics, and then understand what topics we need to improve upon for A-Level Physics. So thank you very much for watching this particular revision session on A-Level Physics Paper 2. Thank you very much for watching and have a lovely day.